All right, so naturally we're studying chemistry, so what we want to talk about is chemical reaction rates. So what we want to know about is the change of concentration of one of our components over time. So change in concentration over some period of time. And so what this double brackets mean, this is concentration. And it's usually in molarity, but not always. So you want to get that symbol down. We're going to be using that symbol throughout this entire course. So from now on, these brackets mean concentration, and whatever's inside of it is what concentration we're talking about. By convention, the reaction or the rate of a reaction is always positive. But what we'll see later on is that the signs of the things here get a little kind of iffy and a little bit arbitrary, but it's not too bad. And when we're talking about the rate of a chemical reaction, it's per chemical reaction. And I'll explain what I mean about that in a little bit. So let's take a look at an example. So here we have H2 as a gas, so hydrogen gas. And then it is reacting with I2, iodide gas, to form HI gas. So always in a chemical reaction, the first thing you should check is the equation balanced? And in this case, it is not, right? You have two hydrogens and two iodides on the left side, but only one of each on the right side. So we need to double the amount on the right side. And the stoichiometry will be important for rates of reaction. So let's take a look at a plot of maybe what this data would look like. So we'll put concentration over here, and we'll say 1 molar up here, 0 molar down here, and then 2 molar up here. And then we'll just put this x-axis as time. And then we'll think about the concentration of H2 in this kind of orange color. And then we'll think about the concentration of HI in this purple color, right? So let's say that we just start off with 1 molar of H2, right? It's going to be formed into products, so it's going to disappear. And the overall kind of reaction is going to look something like this, right? You can see it's non-linear. All of these things are exponential functions, and so they're non-linear, right? And so if you think about the stoichiometry here, for every 1 H2 that you have, you will form 2 HIs. So if you had 1 molar of the H2 to begin with, you would eventually end up with 2 molar of the HI. And so that would look something kind of like this. Let me actually, stuff's gonna kind of get in the way. Move that up there. That would look something like this, right? The formation of the HI is going to be faster than the H2. So when we're talking about the rate, we're talking about the overall reaction. And so we can see that H2, there's only 1 H2 per reaction. So it's going to be the same as the overall reaction rate. So the rate of this reaction is going to be equal to the concentration of H2 over the change in time. Now the concentration of H2 here over time, the change is negative, right? It's getting destroyed. So sometimes you'll see this negative here, sometimes you won't, and instead it's just applied. You just have to remember that the overall reaction rates are always positive numbers. If we think about the rate of the reaction in I2, in terms of I2 here, well, for each reaction, we only have 1 I2, so our rate is going to be equal to the I2 as well. And you can have that negative there or not. And then finally, we'll think about the rate in terms of HI, right? So for every 1 HI formed, you only did half of reaction, right? A whole reaction forms 2 HIs. And so if you have 2 HIs formed, your rate is actually only half of that. And so this rate is equal to 1/2 of the change of the concentration of HI over delta T, right? Because you need 2 HIs to form 1 reaction, right? Because all this stuff is in terms of per reaction. And this part is positive because it's a product, so it's being formed. And you can see over here that this slope is positive. So let's just take a look at some of this, or a set of data here. So we'll have time here. So we have 0 seconds, 10 seconds, 20 seconds, and then 30 seconds. Take a look at the concentration of H2, and it's in units of molarity. So we'll start off with 1 molar, then we go to 0.819, then 0.670, then 0.549. And then let's think about the change in the concentration of H2, right? The change in the concentration of H2, right? It doesn't make sense to have an answer here because we haven't had any change yet. But let's see what happens when we go from here to here, right? What's your change here? Well, if you subtract these two numbers, you'll get negative 0.181, right? You have a change in 0.181 molar of your concentration of H2. What happens when you go to the next step? Well, if you subtract these two numbers, you get a negative 0.149. And then what happens when you go between these two numbers? You get a negative 0.121. And then let's think about the change in time between all of these intervals, right? Ignore that first one. And we can see each time we're only going 10 seconds, right? So the change in time is always just 10 seconds. And so then if we think about the rate is the change in concentration, in this case negative because our rate has to be positive, over the change in time. And so we'll take this 0.181 and then divide it by the 10 and continue on and so forth. So you get 0.0181, 0.0149, and then 0.0121. And so this is not that important of a chart to kind of follow, but really what we want to see here is the rate of the reaction. And we can see it is not constant. It is not constant. At the beginning of your reaction, your rate is fast. And then as the reaction proceeds, your reaction slows down. So the average is not constant. And so in chemistry, this is why we don't talk about the average rate of a reaction, because it's not constant.